we are starting.
Yeah, it's the second part of chapter 2. It should really be a separate chapter, but it's sort of the way it goes.
I was starting with one thing. We're not starting with, we're not having E fields and capacitors.
Yeah, we're sort of moving away from electric fields, okay? So we're not really going to see it again until the final. So that's probably good. I think that's good. That's sort of my least favorite section is the E fields, potential and stuff. So let's move on into capacitors. We're going to look at mainly parallel plate capacitors, which are the primary type of capacitor that we use. And it just consists of two metal plates of an area A. Two metal plates with area, call that A, separated by a distance D. There's a little figure, cartoon of them. Goodness. All right. Now, when connected to a battery, the capacitor becomes charged. And it stores energy that can be used later. So as you can imagine, if you can connect it to this source of a potential, the way we think about this, it's not really what happens, we'll talk about that later, but the way we think about it is that positive charges run along this wire, and then they populate on this plate, and that induces a charge, a negative charge, on this plate. And then if you take that battery away, then it will keep those charges on there until you're ready to use them at some point. Right? So one of the primary uses of capacitors is to store what? Right, to store energy. I want to show you something. This is really cool. I just found this. This is a guy that has, I don't know, there's all sorts of stuff on the internet, but this guy has taken his car battery. You know, a car battery is a device that takes a chemical reaction, chemical energy, and converts it into electrical energy. But he has taken that and replaced it instead with a capacitor. So this is he uses it, he charges it up with his alternator in his car, and so he stores this charge on these capacitors, and then later when he wants to use it, then he has those charges stored on the capacitor, and by engaging the switch, it starts his car, turns his starter and starts his car. Now there's a problem with that. So you might imagine what the problem might be with using capacitors instead of a battery.
Humidity and losing of charge.
Right. So
the dead car.
right. So if you have these capacitors, especially if you just had two metal plates that are out in the air, they would lose charge to the humidity in the air around you pretty quickly. Now capacitors are a little more complicated in that they're wrapped up in insulating material, so they don't lose charge that easily. But he's built this capacitor battery. Now, it's not a battery, it's a capacitor, so it operates by a different principle. But he's built this to start his car. You want to see this? It's kind of neat, actually.
Why don't they do that? Probably make something.
All right.
Very quiet car.
Now, we define the capacitance of the capacitor, and we're going to actually define it in two different ways in this chapter. One based on the voltage and the charge that is on the capacitor, and then later we'll define it by its geometric dimensions. But first we're going to define it by the amount of charge it holds with a certain potential difference between the plates. Or the amount of charge it holds when there is a certain potential difference between the plates. Remember, this potential difference we call delta V, and our charge we're going to call Q. And then based on that, we can define what our capacitance is. Can I go down from here? You can think of capacitance, it sounds a lot like capacity. It's what capacity does the object have for storing charge? All right, so our capacitance then is defined as Q over V. So if V goes up, then our Q is going to go up for a certain potential. If V goes down, then our Q is going to go down. That means if I have more potential between those two plates, then I'll be able to store more charges on those plates. Is that sort of intuitive to you? That if I hook it up to a bigger battery, I'm going to be able to store more charges on the capacitor? Yeah, at a certain time we'll watch a video later where they actually blow up these capacitors, because if you put too much charge on them, the charges will jump across the plates, and that'll cause them to blow up. And there's paper inside them usually that'll burn them. There's about a gazillion videos on YouTube of exploding capacitors. You can just go in and type in exploding capacitors, and people like to do that. The units of capacitance are the farad. This is after Michael Faraday. And a farad then, based on the definition up here, is equivalent to 1 coulomb per volt. The abbreviation for the farad is a capital F. So for the figure on the previous page where I had a 12-volt battery, if I have a potential of equal to 12 volts, then I can calculate my capacitance, Q over V, if I have 24 microcoulombs over 12 volts, and that'll just give me 2 microfarads. Right? Capacitors are usually measured, their capacitance for charge are usually measured in very small amounts. So micro is a very common prefix, metric prefix that we're using. So don't forget your small metric prefixes again. Micro is 10 to the minus 6. Nano is 10 to the minus 9. We're using them quite a bit with capacitors. Also notice that when I use this formula, that I didn't convert this to 24 times 10 to the minus 6. Instead, I just carried that over into my answer. All right, so I mean, you can do that, convert it into coulombs, but it's easier to not, and just carry that micro over into the answer. Y'all clear on what I mean by that? It'll make your math a lot easier. A lot of the math is going to be pretty simple, because it's just sort of simple equations like this, so you want to be able to do it as quickly as possible.
Funny. In our middle school chemistry class, we were messing with batteries and different things. We're making circuits and different things, and someone placed so many different circuits onto one set of a small set of 4 batteries that they blew the wrapping off. The battery started heating up and melted the wrapping off.
Really?
Yeah, it was fun.
Where's my clicker base? I mean, this thing has just messed up my computer. You know, I heard on the news, since you said that you know, when you take these applications, y'all care? It's not related to the class, just take a second. When you take these applications online, they collect a lot of metadata on you, right? Metadata is information that's not particularly about you, but it's sort of like extra information that they collect. So like if you take an online job application, they collect things like where you live, like what's your IP address, what kind of browser are you using, how much time you take in between questions. And they found, these were applications for call centers where people would answer phones, that people that used Google Chrome were generally better employees than people that used Internet Explorer. Like after they hired them, they became better employees. Google Chrome and Firefox actually, Mary. But Internet Explorer were by far inferior employees. I'm not saying that you need to give up Explorer, but all right.
Nothing wrong with it if it breaks down.
Okay, let's try this clicker question. Capacitor C1 is connected across a battery of 5 volts. You have an identical capacitor across a battery of 2 volts. Which capacitor has the most charge? Stop about 35 seconds. I'll stop at 35. I'll stop at 40. Okay, the one with the bigger battery is going to have a bigger charge. Remember, C is equal to Q over V. And so if V goes up, given the constant capacitance, not that goes down, the Q also goes up. If V increases, then Q increases. If you have more energy in your battery, that's going to allow for a greater amount of charge stored on that capacitor, or a greater amount of electrical energy stored in the capacitor. So A is the right answer. Yeah. Oh, it does, though. I'm sorry, one thing. It says identical, which means it's the same capacitance. Okay. If there's any questions about the language or whatever, y'all can always ask me in the test and what have you if you just don't understand. All right. Now let's also look at the geometric proportions. So remember we had two geometric proportions. Do you recall what they were for our capacitors?
Oh, area.
Right, so the area, right, these plates have a certain area, and then they're also separated by a distance d. So I want you to, we're going to try these questions. How do you think the amount of charge is, the amount of stored charge is affected if the area is increased? So if I just take those plates and I make them bigger, how does that affect the amount of charge that I can store? Can it store more, less, or the same amount of charge? We haven't said this, but I think that you probably intuit it. All right, I'll stop at 40 seconds.
I'm pretty sure that
Your intuition is probably correct. Very good. They can store more charge. If I have bigger plates, right, they can store more charges on them. So A is the correct answer. And what if I separate those plates? Like I have two certain plates and then I just pull them further apart. How is that going to affect the amount of charge that it can store? Again, your intuition is probably correct on this. Stop in 30 seconds in 5 seconds rather, at 30. Okay, B is correct. If I pull those plates further apart, it's like it's spreading that energy over a larger distance, and so they're not as able to collect as many charges on them. I'm about to show it to you right now. So from these two expressions, we can say that our capacity to store charge, our capacitance, is proportional to the area. That means if the area goes up, our capacity to store charge, our capacitance goes up, and that our capacitance is inversely proportional to the distance between them. So if you separate them more, then our capacitance will decrease. So we have these two proportionalities, and so we can express the capacitance in this way, that our capacitance is equal to the area over the distance, and we're going to multiply that by epsilon naught, which is called the permittivity of free space. Now this is related to that Coulomb's constant, if you recall. Coulomb, well, we didn't say this, so I'm just going to write it over here. That Coulomb's constant was equal to 1 over 4 pi epsilon naught. We won't use that expression in this class, but you might see it elsewhere outside of this class if you see this material again. So if you have the geometric dimensions of a capacitor, you can calculate what its capacitance is. Can I go down from here? We have two different ways of calculating capacitance. We have the definition, Q over V, based on the amount of charge for a given potential, and then we also have based on the geometric. And there are two independent ways of determining the capacitance. All right, let's try this. you have a capacitor that's hooked up to a battery with a voltage of 12 volts. You charge the capacitor, and then you remove the battery, right? And then I want to know what is the voltage across the capacitor if the area of the plates is doubled. Now, I have Q is equal to CV, and then I have C is equal to epsilon naught A over D. When I remove the battery of 12 volts, this capacitor is going to have a voltage of 12 volts. It has enough charges stored on it so that my voltage across the capacitor is 12 volts. But then, when I change the area, I change the capacitance. When I change the capacitance, that's going to change this, because the amount of charge is going to remain constant, and that's going to affect the voltage. Try it now. I'm going to say that one more time. When I charge it to 12 volts and remove the battery, the capacitor maintains that 12 volts potential because that has energy inside of it. It also has a certain amount of charge based on its capacitance. And then when I change the area, that changes the capacitance. Like after I remove the battery, I change the area, then I change the capacitance. When I go back over here, if I change this capacitance, it's going to change the voltage on that capacitor. I'm sorry? Oh yeah, I'm sorry. There it goes. If you clicked in, go ahead and click in again. This might seem inconsequential, but you have variable capacitors where you can actually change the capacitance of a device, and then that can change the potential that's provided by that device. Stop at 35. Okay, let's see. So if I change the area, so if I double the plates, the area of the plates, that's going to double my capacitance, right? Now over here, I know that this is constant. The amount of charge that's on the plates is going to remain constant. So if I double this, what's going to happen to the potential? Is it going to go up or is it going to go down? And by what amount is it going to go down? Let's try it again. So I'm basically increasing the capacitance by a factor of 2. My charge remains constant because it's not hooked up to a circuit. The charge isn't going anywhere. So what happens to the voltage or the potential? I'll stop at 25. 25. All right, C is correct. Because if I've doubled my capacitance, that means in order to keep Q constant, I have to have my potential, or my voltage. And since it was 12 volts before, that makes it 6 volts here. All right. When you have these two metal plates, it's very important that they don't touch, because if they touch, you're just going to have a closed circuit, and you're not going to have a capacitor at all. And so for that purpose, we're going to have a dielectric. And the dielectric will really serve two purposes. I'm actually going to list the least important first. The least important is to increase the capacitance of the capacitor. All right, so if I have these two plates and they have a certain capacitance, C naught, if I put an insulating material in between them, then my capacitance will be kappa times C naught. So this is my dielectric constant, kappa. Greek letter kappa. This is the dielectric constant. The dielectric constant has to be bigger than what value? No, not 0. The dielectric always increases the capacitance of the capacitor, so it's always bigger than 1, right? So the dielectric constant is always bigger than 1 because it always increases the capacitance of the capacitor. This is just an experimental value. If we want to know the capacitance of, or the dielectric constant, we just measure the capacitance of a capacitor with and without that dielectric. Now, the main purpose, however, is because you want to keep those two plates from touching one another, and so the dielectric prevents that. Because if the two plates touch, then the charges will be able to flow through the circuit. It looks like this. We'll watch a video in a little while of these sort of exploding capacitors. So I have another one I want to show you now. So this is a capacitor. You have these two leads. They sort of look like this. I have one wire that goes to a metal plate like this, and then I have another wire that goes to a metal plate like that, and then they put a dielectric between them, a piece of paper or whatever, like that, and then they roll it up. Y'all ever go to Roly Poly here in Thibodeau before it closed down and became Chubby's, and then became something else, and then became that Boost store? You know what I'm talking about?
What?
Yeah, it was like 12 years ago.
It was a long story that was leading to nowhere.
Right,
Said that it was still closed.
Okay. Anyway, it was sort of looks like that. It was like a roll up, right? So they take that and then they roll it up. There's the one lead. Well, y'all get the idea. And then you have paper in between these two to keep them from touching. I should have two pieces of paper. All right. What's that?
At least it's safe.
Right. All right. Let's watch a little clip. This is a clip from Make Zine. You ever watch that YouTube channel? I think it's actually like an online magazine, and they do a lot of cool circuits things. And this guy is really cool, and it has sort of groovy music too. So he's just sort of talking about the and you can even like build your little capacitor inside a big box so that people could look in the hole and see the sparks fly, that kind of stuff. I think that'd be kind of cool. All right, let's try this. It's a simple calculation, really. About 10 or 15 more seconds. Stop at 235. 235. I think that's right. Let's just take a look. So let's see. So 5.3. As I said, this is just a simple calculation. C, based on this definition, is equal to kappa times C naught. And so we need to find C naught, which based on our definition is epsilon naught A over D. So that's going to be, what's this, 8.85 times 10 to the minus 12. A is in 0.4 meters squared over the distance, which is 1 micron, or 1 times 10 to the minus 6 meters. Notice that I do need to have everything in SI units for this. What is that? Does anybody know? Have that written down? Yeah, what's that answer for C naught?
It's A.
Well, this was 3.5? Okay. Yeah, so it's 3.5 times 10 to the minus 6 farads. But then we increase it by a factor of 1.5. So I say 1.5 times 3.5 microfarads, and that gives us 5.3 microfarads. All right. Since I told you we'd see the exploding capacitors, let's take a look at that. Y'all clear on this? It's okay? Before we're about to... Right, let's move on to circuits. I'm going to just show you some of the basic symbols that we're going to use, and then we'll look at capacitors in parallel. In the next 3 chapters, we're going to look a lot at circuits. So we'll be using these symbols all throughout. The symbol that we'll use for a battery will look like this. Sometimes we'll use a symbol that might be a little bit differently. Like, for example, we might add some stuff to this. Like, for example, I might put a plus and a minus there. That just shows what's the positive terminal and what's the negative terminal. And then often we'll list the voltage of the battery below it, something like that. Capacitor, the symbol that we'll use will look like this. It looks like sort of our cartoon capacitor, where we have those 2 parallel plates, a parallel plate capacitor. However, another symbol that you'll often see, and there's really no difference in them, but you can have a capacitor that looks like this. That's also a capacitor. So you might see that in other circuits as well. And often if you get electrical devices, if they have circuit diagrams with them, you'll see these symbols. Capacitors are directional. I'm not sure what about them makes them directional, like inside of them. Like if you remember in the video that we just watched, they said that the way they got them to explode was to do what? They reversed the lead, so they put the negative to the positive and the positive to the negative. But I don't know why they're directional. I'm trying to find out. But anyway, this symbol helps you to see the direction that the current is supposed to go, or the way they're supposed to be hooked up. And then the resistor looks like this. It's just a squiggly line. All right, so let's look at combinations of capacitors. Just have a few minutes left, but I will just want to go over capacitors in parallel. Can I go down from here? So you can connect capacitors either in parallel or in series. Most of our circuits are not most, but some of our circuits are going to be fairly simple, and it'll be very obvious what's in series and what's in parallel. But some of them will be a little more complicated, and it won't be so obvious. So there's a good way to tell if something is in parallel or in series. These 2 capacitors are hooked up in parallel or in series. Just from the words, what do you think? All right, these are in parallel. They run parallel to one another. The way that you can tell is if you come along in the circuit from some direction and you come to a point where the circuit breaks into 2 pieces, then you know that that circuit is in parallel because it breaks into 2 pieces. And as I said, this seems obvious here, but we'll see some circuits where it won't be so obvious that it's in parallel. These capacitors, as you might guess, are in series. And the way that you know if it's in series is you come along here and you don't see any break in the circuit. All right. So let's look at capacitors in parallel. Can I go down from here? So they'll look like this. I'll have a battery. I'll have two capacitors. This has a voltage V. We'll say this has capacitance C1 and that has capacitance C2. A few rules that we're going to come up with for capacitors in parallel, and we'll have similar rules but different for capacitors in series, and then next chapter when we get into resistors we'll have even similar rules. So capacitors in parallel have the same voltage across them. So if the two capacitors are different, then they have different charges stored within them. So say, for example, if this is 12 volts, then I'm going to have 12 volts across this capacitor, and I'm going to have 12 volts across this capacitor. Capacitors in parallel have the same voltage. And that's going to be our first rule. Capacitors in parallel have the same voltage. Right, those two capacitors are in parallel with one another. With the battery. They're in parallel with the battery. Alright? You can think about this as if they're hooked up directly to the battery. Whenever you have things that are hooked up in parallel, they basically look like this. This isn't a circuit diagram, it's just sort of a sketch. If I have a battery here, I can hook up a capacitor to it, and if I have 12 volts here, then I'm going to get 12 volts across that. And then you can also imagine that, well, what if I just hook up a separate capacitor that's also in parallel? Then it's also going to run those 12 volts. So I like to think about it as I have two independent circuits that are both hooked up to the same battery, and then they run the same voltage, which is the voltage of the battery. All right? So the first rule is capacitors in parallel have the same what? They have the same voltage. Capacitors in parallel have the same voltage. That'll be true for resistors too in the next chapter. But capacitors in parallel have the same voltage. All right. I think we'll pick up with this example next time. Okay. Y'all have a great day. That's all.
So